image and see theory in effective safety. This.
Thank you very much. I'd like to thank the organizers for the invitation to this wonderful workshop. Today, I'd like to talk about some defect CFT, basically the conformal theory with defects, and some properties of entanglement, entropy, and free energy. And also, I'd like to talk about some implication for C theorem. So this talk is based on my paper with Nozomu Kobayashi, a grad student in our group, and Yoshiki Sato in the audience, and also Ken Watanabe, a postdoc in our group. So this is an outline of my talk. So first, I'd like to briefly review what the defect conformal theory is, and then I'd like to move on to the story of entanglement, entropy, and the sphere free energy in DCFT, and I'd like to also conclude with some speculation about the C theorem in DCFT. So okay, so when we say that the defects in QFT, so which basically means that they are just non-local objects. So all possible objects which is non-local can be called defects, basically. So there are many examples. So in one-dimensional case, so they are called line operators. They are just Wilson-Tofu operators. And also there are so-called surface operators, which is two-dimensional. And more famous examples are, say, domain walls and also interfaces. Also, boundaries can be regarded as a complementary one defect, or boundaries. And basically, so they are defined by the boundary condition around them. So just imagine that this is a Tofu's loop. So to specify the Tofu's loop, so you measure the flux around them. So this is a three-dimensional space, and you have one-dimensional line, and then you can cover this operator by two spheres, so you can measure the magnetic flux through this Tofu's line. So this is the definition of the Tofu's line. And similarly, so the interfaces are characterized by specifying the two theories, and on the left-hand side and right-hand side. So this is basically the notion of defects. And there are many types of defects, but in this talk, I'd like to focus on conformal defects. So I'd like to focus on Euclidean case. And in this case, so without defects, the conformal group is SOD plus 1, 1. So this is just a conformal group. But if we have a p-dimensional conformal defect, so which I denote by script dp, then so I want to preserve maximal symmetry inside conformal group. So the defects should be either flat or spherical. So then you can preserve a maximal symmetry. So basically, you just imagine that you have flat defects. Then you can preserve the conformal symmetry on the defect, p-dimensional defects, which is SOP plus 1, 1. And then, so because this is flat, so you have rotational symmetry around the defect. So then, so the rotation group is just SOD minus P. So this is the maximal symmetry you can preserve in the presence of p-dimensional defect. And then, so okay, you can decompose the space-time along the defect and also transverse directions. Then, so interestingly, so defect allows a defect local operators, which are supposed only localized on the defect. And the interesting thing is that, okay, once you focus on the conformal defect, then you can constrain the form of the probation function just only using the residual conformal symmetry. So here is an example. So let's first start with one-point function of scalar primary. So this is the bulk operator, scalar primary in the bulk. Okay, so basically x is away from the defect. Then the one-point function is completely fixed by the conformal symmetry. So basically, so you just have a one scale, so which is just the length distance to from the defect. So x perp is just a transverse coordinate. And then the 1-point function, if this operator has component dimension delta, then it is completely fixed by this form. You have one unknown constant, AO. So just only using the conformal symmetry, so regular conformal symmetry, the 1-point function of scalar is fixed. And similarly, so let's move on to the stress tensor. So stress tensor also completely fixed by just using conformal symmetry. And there is only one term, so one constant, AP. So this constant depends on the types of defects and also the bulk series also. But from this form, okay, so yeah, you can see that when P, so the dimension of the defect is D minus 1. So namely, so if you have, say, boundary safety or also interface safeties, then the 1-point function of the stress tensor actually vanishes. So in this case, okay, this is very similar to the theory without defect. So now, so the goal of my talk is that basically I'm interested in how entanglement entropy is modified due to the insertion of defects. And also I'm interested in the sphere free energy. The sphere free energy is just a sphere partition function, it's a Euclidean sphere partition function in the presence of defect. So I'm going to think about the entanglement entropy of some spherical region, and I put a defect in a very symmetrical way. And also when I consider the sphere free energy, I put a conformal defect along, say, equator. And now, so I ask 2 questions. So basically, they are mostly the same. So how do they depend on defect data? And also, how do we count the measure degrees of freedom associated to defects? So, okay, so now let me move on to the second part. So let me briefly remind you how to define entanglement entropy. So first, without defects. So to define entanglement entropy, we basically take a time slice, say t equal to 0, and we divide a space into 2 regions, A and B. And now, so we define entanglement entropy as a von Neumann entropy for the reduced nature matrix. So this reduced nature matrix is defined by just taking the partial trace of the total nature matrix. So you integrate out the information outside the region A, then you get the reduced nature matrix. And I'm going to focus on just a pure ground state. So I only talk about pure ground state. So then, okay, so this definition is very general. So, but now, so we want to compute it in quantum field theory. So it's actually easier to introduce so-called the reigning entropy. So reigning entropy is a one-parameter generalization of the entanglement entropy. And if you take n goes to 1 limit, so you end up with original entanglement entropy. But the reigning entropy is actually easier to compute in QFT because so you can use so-called replica trick. So even if you start with just a flat space without any defect, when you calculate the reigning entropy, so you need to consider so-called the n-fold cover, which is branched over the region A. So this is actually the time direction, and this is space direction. And if you have a region as an interval, then you have to consider the so-called covering space of the original, say, 2-dimensional sheet. So this is just a n-fold cover, just a Riemann surface with cut, and these are glued together. And so basically the computation of the entanglement entropy amounts to calculating the Partition function on this space. So even if you start with, say, flat space, you have to deal with the quantum field theory on a manifold with singularity, so which makes computation very difficult. And only only few examples can be computed exactly. So for instance, so if the theory is free, and if the shape of the region is very, say, symmetrical, then you can get exact answer. But otherwise, there is no way to calculate it, even Okay, let's focus on the CFT, and let's pick up, say, spherical region as our region A. So in this case, since this configuration is so symmetric, so there is a nice conformal map, so which maps, say, the n-fold cover in the previous picture to a sphere. So actually, the n-fold cover of a sphere. And so this is slightly unfamiliar form of the sphere. So you first start with, say, time direction and also the polar coordinates in the spatial region. And you make a conformal map. And then, so it ends up with some unfamiliar form of the sphere. So under this map, so originally, so we had a orange curve, which is the boundary of the region A. So this one is actually the d-2 sphere. Now, which is now mapped to d-2 sphere inside the d-dimensional sphere. So now I'm talking about the Euclidean theory. And so this sphere is located at the theta equal to 0 in this figure because it is codimensional 2, so it should be located somewhere at a constant theta. And also, so now we also have to take the n-fold cover along this blue curve. So this blue curve has a linking number 1 to this orange curve. And this blue curve is now mapped to another circle, which I parameterized by tau. So this is highly non-trivial map, but anyway, so once you map the n-fold cover of the flat space using CDHM map to the sphere, then now it's actually very easy to realize the n-fold cover. You just scale the periodicity of tau from 2 pi to 2 pi n. And since CFT is supposed to be invariant under the conformal map, so the partition function should be invariant under this map. So originally, so we have to compute the partition function on the n-fold cover of the flat space, but it ends up with the partition function on the n-fold cover sphere, SMD. And now, so you have you change the periodicity from 2 pi to 2 pi n. So now, so of course, I assume that there is no conformal anomaly in this argument. But if there is an anomaly, then you also have to take into account the anomaly, conformal anomaly, under the map. But anyway, actually the Renyi entropy end up with this form. So Renyi entropy across a sphere in CFT is given by just computing the CFT partition function on the Euclidean sphere. But this sphere is now n-fold cover. But you can show that when n goes to 1, then the entanglement entropy becomes equal to, actually it equals to log of the sphere partition function. Okay, so this is very beautiful result. So in n goes to 1 limit, so you can show that up to UV divergence, entanglement entropy is nothing but the sphere partition function. So this is a remarkable result. And now I'd like to generalize this argument to the theory with defects. Now I put a defect, three-dimensional defect, in the kind of a center, some symmetric location. In this figure, so this defect is just one-dimensional, so I insert it at the origin. And I also consider the spherical region A. And you can still use the conformal map, the same conformal map as before, even in the presence of defect. And then, so since you put a defect in the symmetric point, so it's actually easy to generate the previous argument. And then the Renyi entropy in the presence of defect becomes actually it takes the same form as before, just the CFT partition function replaced with defect CFT partition function. Okay, so basically you are supposed to compute the partition function on sphere of the CFT. But this quantity includes a contribution from defect and also the bulk CFT. So it's reasonable to subtract the bulk contribution from the entanglement entropy in DCFT. So we call it defect entropy. So this is just the excess of entanglement density. So we want to count how much entanglement density comes from the defect. Okay. And on the sphere, on the airport sphere, so the defect is located at the equator, some symmetric location, and you take the airport cover along this circle. And actually, so this defect entropy can be written using the web of the defect. So yeah, after some simple computation, so it becomes, so it is actually given by the web of the defect operator on the airport cover of the sphere. So this web is defined by the ratio between the partial functions in DCFT and CFT. Okay, now, so we are interested in n goes to 1 limit. So let's take n goes to 1 limit. So actually, so on the sphere coordinates, so actually it's easy to take n goes to 1 limit. So first you expand the sphere metric. Okay, sphere metric is very close to the sphere, and so the deviation of the metric is just order n minus 1. So you can expand the partial function with respect to this small part of the equation. And then the first leading term is given by a t mu nu times the variation of the metric on the sphere. Okay, so this is just the order n minus 1 term, and only this term contributes to the entanglement entropy. So the higher order term does not contribute. So without defect, so we know that the 1-point function of the stress energy tensor vanishes because of the conformal symmetry. So we recover the previous result. Okay, so the entanglement entropy actually becomes log of the sphere partial function. So it's because the t mu nu, the 1-point function t mu nu vanishes. But in DCFT, so t mu nu, so 1-point function t mu nu does not vanish. Actually, it can be fixed by conformal symmetry up to one constant, AP, but it doesn't vanish. So there is some contribution from this term. So it's not difficult to evaluate the contribution from this term, and using the dimensional regularization. So we found that the defect entropy is now given by this. So the leading term is given by log of the web of the defects. Okay, but there is a contribution from the second term, so which is proportional to 80. So this is universal results, which is valid for any CFT. Okay, and of course, so this equality holds up to UV divergence. So in this argument, so we use dimensional regularization. So all the power of that UV divergences are kind of cancelled. Okay, renormalized automatically. And our formula, so our result actually reproduces a well-known result when p is equal to 1. So when p is equal to 1 case was studied by Rupert-Spancer. And also there is one more thing. So here, so this second term actually vanishes when p is equal to d minus 1. So this term vanishes. So which means that in this case, so when the defect is codimension 1, the defect entropy is equal to the sphere partial function. Okay. And also there are, okay, using dimensional regularization, so you can see that so there is a pole coming from this sign factor. So when p is even, then so this vanishes. So there is a pole, which means that there is a conformal anomaly. So when the dimension of the defect is even. So this is a conformal anomaly associated with defects. Okay. So now let me move on to the story. So now we want to consider the C theorem. So before moving on to the C theorem in DCFT, So let me briefly remind you what the statement of the C theorem is. So C theorem can be stated as follows. So basically, so we want to, okay, so given a pair of series which are connected by RG flows, let's say so TUV to TIR. So suppose you have a RG flow from UV CFT to IR CFT. So then C theorem states that there exists some function, so which decreases along RG flow. So which means that okay, this is a space of QFTs, and here we have a RG flow, so from TUV to TIR. So which okay, the C theorem means that there exists some height function on this space of QFTs, and such that okay, when RG flow is triggered, then this function becomes lower and lower. This is a statement of C theorem. And of course, okay, it's very hard to find such a function because you have to construct universal function, so which on the space of QFTs. So this is highly non-trivial statement. But if such a function exists, then you can regard it as a measure of degrees of freedom in QFT. So naively, so intuitively, so if you go to the higher energy scale, then there are more and more degrees of freedom. But if you go to the higher regions, then massive degrees of freedom decouples from the theory. So the number of degrees of freedom is supposed to monotonically decreases. And there are many examples of the C theorems. The most famous one is the Roscoe C theorem in 2 dimensions. And also in even D dimension, I'm counting the Euclidean space-time dimensions. So they are called A theorem. So A theorem uses a type A anomaly. So this is a conformal anomaly. You can pick up the type A anomaly by computing the one-point function of the trace of the stress tensor on sphere. And then, so A anomaly is supposed to be a C function. So on the other hand, so in odd dimension, there is no conformal anomaly, but there is a very interesting proposal known as F theorem. So F theorem also uses a sphere partition function as a measure of degrees of freedom. And there are interesting proofs using the monotonicity of entanglement entropy when these less than or equal to 4. But all of these can be generalized to a sort of a generalized F theorem conjecture. So this conjecture is to my best knowledge, this is the most general conjecture for the higher dimensional C theorem. So first, you define F tilde by multiplying some sign function to log of the sphere partition function. So then, so the conjecture states that F tilde is monotonic and the RG flow. So that means if you compare the fixed point values of F tilde at UV and IR, then F tilde UV is always greater than FIR tilde. So why is this conjecture so interesting? It's because it interpolates between F and A theorems. So when these are, then it reduces to just a sphere partition function. So this is known as the F theorem. So on the other hand, so when these even, so naively, so when these even, sign function vanish. So F tilde becomes 0, but there is actually conformal anomaly coming from the sphere partition function, and they cancel to each other. And then you can extract the A anomaly from this F tilde. So using the dimensional regularization, so you can see that when these even, the F tilde becomes proportional to A. It's an A anomaly. So this is the status of the C theorem without defect. But now, so let me move on to the C theorems in DCFT. So when the bulk dimension is 2, so just consider say 2-dimensional boundary CFT. So then, since you have a boundary CFT, you have a boundary which is 1-dimensional. So this is a 2D bulk and a 1D boundary. In this case, So there is a so-called G theorem. So this is an analog of C theorem in the boundary CFT. And there are two types of proofs for the G theorem in this case. And there are also very nice a proof of so-called B theorem. So when the dimension of the defect is 2, then there is a B theorem. This is also an analog of C theorem in direct CFT. But in this case, the bulk spacetime is the dimension of the bulk spacetime is arbitrary. So you just couple some 2D theory to higher dimensional bulk theory. Then so there is some sort of B theorem. This is also proved. But there are several proposals in other dimensions, in other cases. So in 4D and in boundary, okay, in 4-dimensional boundary CFT, so it is proposed that by this gentleman that there is some so-called boundary epsilon. So they argue that the sphere partition function 125 decreases under any boundary RG flow. But in other flows, so there are no proposals. Okay, so there are no proposals in these shaded regions. So we want to fill these slots somehow. But okay, but there are two natural candidates for the C functions, okay, which was actually used in the literatures. So one is entanglement entropy. So using entanglement entropy is very natural, at least from the holographic perspective. And another candidate is using sphere free energy as a measure of degree of freedom. And yeah, the boundary epsilon actually also uses sphere free energy. So these are very natural candidates for the C functions. And so these two actually agrees when P is equal to D-1. So namely, so if we have co-dimensional defect, then both agrees. So these two agree due to our results. So you cannot distinguish them. But when the dimension, dimension of the defect is general, in the general case, so P is less than E-1, then so these two differs. So the question is, are those C functions for any D and P? So they could be C functions, or maybe both of them are not. Okay, but now, so we conjecture that, okay, now we make a conjecture. So first, we consider so-called defect RG flow. So defect RG flow means that basically it's a relevant perturbation. But the relevant perturbation is now restricted to the p-dimensional defect. So you have a defect local operators OHAT, and you trigger RG flow in this way. So under such a RG flow, so we conjecture that d tilde defined by this is a C function. So d tilde is now given by the sine function times log of the wave of defect. Okay, now you can compare it with the generalized epsilon. So in the case of generalized epsilon, so we have sine function times log of the sphere partition function. But now, so we replace the sphere partition function with the wave of the defect on the sphere. And we replace d with p. And we argue that this d tilde is a good C function. And we make a lot of checks for our proposal. And actually, all the examples are consistent with our proposal. On the other hand, so entanglement entropy, so there are some counter examples for using entanglement entropy as a C function. So entanglement entropy does not necessarily decrease under defect RG flow. So there are several counter examples we found, and also other people also found counter examples as well. So in general, so the defect entropy and the sphere, the sphere free energy, defect sphere free energy are defined due to this term. So this term does not have any Monotonic properties under RG flow. So due to this term, So entanglement entropy cannot be a C function. So at least, okay, we do not prove our conjecture, but at least you cannot use entanglement entropy as a C function. Okay, so now let me summarize my talk. So we found a universal relation between entanglement entropy and sphere free energy in CFT with defects. And we also propose a C theorem in defect CFT. So our proposal is that just put a defect CFT on sphere and use the sphere partition function as a measure of degrees of freedom. But we don't have any proof for that. So as a future work, so it would be interesting to prove it, say, using supersymmetry. So in the case of, say, A theorem or F theorems, then there are proofs based on the SUSY techniques known as F and A maximizations. So it would be interesting to generalize these techniques to defect CFTs with supersymmetry. And also, G theorem has a nice proof using entropic inequalities of entanglement entropy. So maybe you could, it's possible to prove our conjecture using the monotonic properties of entanglement entropy or sphere free energies. And it is more interesting to constrain the dynamics of defect energy flow. Okay. Once you believe our conjecture, then maybe you can constrain the energy flow itself. Okay, maybe our conjecture gives some non-trivial constraints on the dynamics of energy flows. Okay, thank you very much.
Okay, another question since